You've seen most of the talk, so we can go through this real quick in previous slides. But actually, I'll run through some of the things, point out some interesting points that haven't, I think, get lost in some of the bigger points that I think are important in the discussions and thinking as we go forward. And then I'll talk about some more recent, as Paul mentioned, recent results that I think are interesting, and we're in the process of writing them up right now. As you know, LCROSS was a mission that was a secondary. It was really a mission of opportunity. It was relatively inexpensive. It was $79 million total cost. We gave some money back. We came in under. There it is with the LCROSS spacecraft, and I think in one of the renderings it showed the MLI gold. So, I think it might have been Tim's or somebody's. Still in orbit around the moon. Here's the LCROSS shepherding spacecraft, for all we know, still on the moon. And we impacted, what we crashed into the moon was this part of the Atlas V rocket. This is the upper stage, the Centaur. It was about 2,500 kilograms, empty, and we went to, and we can talk about it offline if you like, extraordinary efforts to keep it empty and clean and baked out and all that stuff. The key characteristics that we've talked a lot about them here for potentially harboring volatiles of all sorts. And I remember we were really banging our heads where to go. As a PI, all the engineers wanted to know where you're going to impact, and I kept putting them off, because LRO was there and getting, increasing our knowledge about the moon exponentially week to week. And, when we first sat down to talk about this 2 years before the impact, we all agreed, definitely don't go into Cabus. It's way too deep a hole. No one can see in there. Never, never, never. But then everything pointed to Cabus as the one certain place there was a lot of hydrogen. And I remember Dave Page gave me some very sagely advice. Just hit the coldest place you can, Tony. I mean, we don't know any more than that. And I'm like, all right, good enough. So dark, cold. This was really important. We actually had some requirements that we had to be guided by the neutron observations. That was to keep us from just targeting Apollo sites or something, I don't know. And topography, we really were interested in, again, this relates to cold, but areas that might have been the coldest places within a PSR. This is where we impacted. It's kind of hard to see here. It looks better on my screen. These are near-infrared images taken from our near-infrared camera. At the very end, our project scientist, Kim Meniko, set the gain to the camera so we could image inside the PSR. These were the first images in Cabus, and I haven't seen anything yet from Mark yet. Cabus is kind of hard to image because it doesn't get a lot of scatter into it, so it is one of these darker places. And you can see here, this is just saturation, when the camera's saturating and pixels are bleeding into each other. But we were able to image and go into this really dark place. I'll talk about that a little bit more later. And I organized the next series of slides I'm going to run through kind of quickly, just kind of from impact on what we sort of saw and what it tells us potentially about volatiles and water at the Cabus site, and ultimately relate that to what it means maybe for the rest of the moon. Right at impact, we saw thermal flash, and I'll talk about the near-infrared spectrometer thermal flash, but this is the mid-infrared camera observations, and I'm always still impressed by this. We were about 600 kilometers away from the moon when we made these observations, and this is just one of these little microbolometer cameras. It worked out pretty well. We saw about a thermal plume emerging about 4 kilometers across, about a second after impact, and this is, of course, real-time data downlink, so all of our imaging is got to be at a rate that is commensurate with our data link. But you can see it after about 7 seconds fading away. It definitely shows some non-uniformity to it. And I showed these gunshots that Brandon Hermelin has done at the NASA gun range at Ames, because I think this is really important when we try to interpret the LCROSS results. We saw this large thermal plume. This is most likely coming from hot debris from the impact itself. It was a slow impact as impacts go. 2.5 kilometers per second is slow. It's not generating a whole lot of heat, and most of the heat's actually in the impact material, the impactor material itself, the rocket bits and pieces. And those are flying off in all different directions. This shows a near-infrared camera image of a gunshot, and you can see right after impact the hot material expanding outward, the plume expanding outward, but then you can see all these fragments and bits remaining outside the crater. So this is the final crater area, this little dotted line here, and you can see how much of the material, hot ejecta and that's mostly the projectile material going outside the crater. So when we think of what LCROSS did, it made about a 20 to 30 meter crater, but actually the thermal impact and the agitation went out kilometers to either side of that impact site. Rate at impact, so this is really went preceding the earlier slide. We did make measurements of the flash in two different ways. One with a visible flash radiometer that measured the total visible flux, and it was down to about a nanowatt. It was sensitive down to about a nanowatt total power to the detector, a little less than that. It measured about 400 hertz. It basically saw nothing obvious in the signal. We also measured it with one of our near-infrared spectrometers. We could change the setting and make samples very quickly at about 70 hertz in 6 different channels. And this shows one of those channels, and it shows the rise from the impact. This is the thermal flash, and it tapering down to then this is ejecta starting to come into the field of view, and we're seeing near-infrared scattering. What's interesting about this is for a thermal flash like this, it's quite broad. The rise time's slow, and the total width of that flash is broad, suggesting that the material we impacted into was not as not as dense, less porous than Apollo-like samples. Pete cited about 70 or 80% in the Science article, and that's consistent with some interpretations of LRO lamp observations of PSR areas. Talking with Phil Metziger, there's a lot of ideas. I mentioned this later, why this could be, that potentially the lack of thermal cycling in the PSRs leads to a very different regolith quality or character than what we saw at the Apollo sites. And that might be interesting and important to keep in mind. So the rest of the LCROSS observations, I always use this. You guys have seen this talk before, and you're probably sick of this particular figure, but it's a nice summary of what we saw in terms of road mapping the observations we took. This is the ultraviolet visible spectrometer as a function of time relative to impact, and you see the impact. We see the ejecta curtain come up. This is all ejecta, or sunlight basically reflecting off of the ejecta. The field of view of the spectrometer is entirely in the dark area, the permanent shadowed region, so all it's seeing, minus scattered light from off-axis sources, is ejecta scatter, and it comes down. Then you see this kind of delayed or continuous ejecta or source here, and then finally we're plummeting down down into the ejecta itself at the very end. And this is explained pretty well with the 2 Plume model, where you have a high and a low ejecta angle plumes. The low ejecta plume is predominantly the source for this this scatter here, and a higher angle plume continues out further. It's nearly constant because it's filling our aperture, our field of view. So as we're approaching it, the flux basically is constant, the flux density is constant, until finally we start to fall into it. Key takeaway, and I'll bring this up later, is 3-4 minutes after the impact, we're still seeing ejecta in our field of view. And there's now ground-based observations that have confirmed that as well. So at that point, this shows this in a little bit different way. Here's the radiance difference of the ultraviolet visible spectrometer as a function of wavelength. What we've basically done is take spectra and difference it from the pre-impact reference, which is entirely in the PSR as well, so it takes into account scattering as best it can and whatnot. And this shows the integration time. So this red just integrates right about the impact itself. So it's catching the actual flash of the impact. And then these later ones are 1.1 to 3.1 seconds. This is from Pete Schultz's paper again. And you can see the rise, you see the scattering of the dust, and you see all these nice emission lines, and a cosmic ray hit there, and a cosmic ray that hit there. But Pete's identified a lot of these different bands. I analyzed the sodium band right here, the emission here, and plot it here, and you can see the rise in sodium after the impact, and then the fall away. Rosemary Killian made similar observations from ground-based observations, got similar results, and we basically doubled the sodium atmosphere with the LCROSS impact that day. And in about 4 minutes, it was back to normal. So that's an important concept to think about, too, in terms of distribution and history of any molecule hopping around the surface of the moon. So during this brightest portion of the ejecta curtain here, we really had the peak visible radiance, and I've already mentioned this tail of two plumes, the high and low angle plumes. This is also where we see the very earliest ice water detection, and I show this plot. Little story between the reviewing process I mentioned to somebody out there. We originally only wanted to talk about the key species of interest for HOMD and AES, ESMD at the time, which was water, OH, and whatnot. But to get this published, they said you had to put in every possible thing you might think might be there. So that's why we have everything in these charts. This was a clear water ice detection right through here and this large band right here for 2 microns. And this is pretty important because this is a strong signature. It's in terms of its depth, and it's probably associated with the lower angle material, which is coming from deeper parts of the impact, and this will come up again later on. I think that's important. As we flew down towards the plume, you saw that long continuous curve. We continue to monitor for water vapor, and you saw this plot a little bit ago. This is time relative to impact and the absorption strength of the 1.87 micron water vapor band. And it seemed to grow, which was surprising to us. We thought we should see it peak and then come back down. But again, that gets back to this whole scavenging concept I mentioned, where this impact's blowing little holes everywhere, like a shotgun kind of over across many hundreds of meters diameter, perhaps, or radius in the area that we're looking at. What supported this evolution, this increase of water vapor, is further analysis of the ultraviolet bands, the OH bands, and the UV's ultraviolet spectrometer. This shows wavelengths versus the ratio radiances. And these are a variety of time periods in seconds averaged. And this shows a little bit later in the mission, about 170 and on seconds in the mission. And it's overplotted against OH prompt and OH fluorescent emissions, which have very different characteristics to themselves. And you can see if we do a nice average to get our signal to noise up, this black line here looks quite a bit like the OH prompt emission, which is associated with the dissociation of water vapor, whereas this OH fluorescent could just be the release of OH bound in the grains themselves, or being desorbed from the minerals as we're impacting and raising their temperatures to about 800 or 900 degrees centigrade. So that's, you've probably all seen that before. This is some more recent work that we're writing up right now, and it has to do with one of the other near-infrared spectrometers that didn't get a lot of attention at first. It was looking off to the side at the sun in occultation. So we had this wild idea that maybe the plume will last long enough we actually fly through it. And let's monitor the sun as we go through the plume, and because the sun is so bright, we'll have a lot of signal to noise. We can look for very small concentrations. So we use this, it is basically a copy of the nadir viewing near-infrared spectrometer, what we call the NSP1, but it was solar viewing. It basically had identical wavelength range and resolutions. It used a diffuser to look at the sun during descent to the surface. I'll show a picture of it. It's just a block. It's very simple and stupid looking, which is good. It's a fiber-fed instrument, so it used this diffuser so it could pick up the sun basically wherever it was on the horizon. Remember, as we descended, LCROSS had to keep our medium gain antenna to Earth. Our spectrometers looking at the impact site, so we were heavily constrained in the exact orientation we had to be in. Our solar panels, we were running off batteries, so we didn't care about that at all. But the sun might have been anywhere within basically a certain number of degrees of our descent angle. And we couldn't designate the launch date, LRO did, so we had to build this diffuser so that it could accept sun no matter where it was in the sky, and we did that. And you'll see the field of view of it is very large for that reason. It was very Lambertian. We characterized it very well, and this is what I just described, so it could support a range of these angles to the sun. Luckily for us, though, for our impact date, just by chance, we were very small, within 14 degrees basically, and constant. Changed much less than 3 degrees during the entire descent. For the entire descent, it changed less than 3 degrees, and of course at the very end it changed much less than So by viewing the sun, we get this high signal to noise. This shows the radiance on the left. These are actually, there's 5 spectrum, each of 0.6 of a second, overplotted on top of each other there during descent. And you can, they're right on top of each other. That's the signal to noise, how good it is. And on the right, I've calculated the signal to noise for these spectra. And you can see we typically have over 500 for most of the spectra of interest. This is a function of falling off radiance, the drop in instrument performance. But that was the point, was we get really high signal to noise for these scans. And these are individual scans, so you can build the signal to noise more by co-adding and averaging, et cetera, et cetera. So there's the NIR near-infrared spectrometer, and then here is the solar diffuser with its fiber that runs over to the spectrometer on the deck. Again, it's, you know, Home Depot part almost. So as I mentioned, we were looking at this high-angle impact plume, and the idea was, gee, will there be actually this dust up there that we possibly fly through? And this idea of a high-angle plume came actually very late. We had this idea before we did some of the hollow gunshots that Pete Schultz and Brendan did, and we weren't sure exactly what we would see during the impact, but we kind of went in with our eyes wide open, not knowing exactly what we were going to see. And indeed, we saw this flux-looking nadir that, you know, continued on, and I'll show you that the near-infrared spectrometer looking at the sun also saw it. And what we basically determined that it would have to, you know, at impact, material getting up had to have reached about 12 kilometers above the surface to still be falling down with us 4 minutes after the impact. So this is what the orientation, if you will, of the near-infrared spectrometer viewing the sun as it came down. This shepherding spacecraft came down 3 kilometers away from the Centaur impact site. There's a lot of discussion and reasons why we impacted not directly on top of it, but downrange a little bit. And this shows actual, this is Goldstone radar images of the LCROSS impact site, and they were able to pick up the LCROSS impact before and after. This is in a paper by Will Marshall et al. And maybe we saw the shepherding spacecraft impact site, but that is much less statistically significant as the Centaur, as you might imagine. But we knew exactly, basically from our trajectory analysis, where we impacted, and so we basically impacted about 3 kilometers away and kind of parallel to the sun, if you will. And the field of view looks like this. It's, like I said, a large field of view, but the sun was basically directly or within a few degrees, or 10 degrees of where we were looking along the sun line here. So we're not looking, you know, it might have been optimum if we came down here and looked through all the cloud, but the point being here is that cloud that's coming down, anything has to be at least 3 kilometers away from the impact site for us to see it. So what did we see? The way we approached this analysis was we took spectra as we descended. We could build a very nice clean reference of just sun, and then we started differencing spectra from that reference. Is it changing? And what I'm showing here is the reflectance, reflectance minus average reflectance. It really should be not reflectance, but total incidence. And as a function of time that I've converted into approximate altitude above the surface, and this is again functional wavelength. The black curve here, the dash curve, for example, is at about 46 kilometers above the surface, and you see it's relatively flat within the noise limits of the instrument here. Likewise, at 41 kilometers, that's this blue line here, and it's relatively flat. The instrument, again, response function gets very noisy out here, so we generally disregard that unless you build up huge signal to noise. As you come down, though, around 36 and maybe 28 kilometers, you start to see this drop. And in particular, you start to see a nice little chunk taken out right here. And then as you get deeper, 21, 16 kilometers, you start to see the entire continuum start to come down. You start to see a band forming here. This deepens. 11 kilometers, it deepens more. And then 6 kilometers above the surface, you have this dip here and this large chunk taken out there. And we fit that using a linear fit, and we can get into the statistics, the chi-square of our new statistics here to say whether or not these are real. These are all what's shown here, basically, except for the C2H4, 3 sigma plus, using a chi-square nu limit in terms of goodness of fit. And what we show here is basically water ice, water vapor, hydrogen fluoride, and that's about it, at least for these components here in this particular fit. And so that's just doing a linear fit. So that's just taking, and that's totally appropriate for an optically thin medium like what we were looking through, just to get a total mixing. But we wanted to do a little better. So from that, you could actually derive total quantities pretty easily. But we want to do something better, so we built a Monte Carlo simulation where we basically simulate a dust cloud that we're looking through towards the sun, and we can put in any kind of particles we like of dust, water ice, any gases, et cetera. And we did a variety of fits in it. We were able to fit quite nicely the data. This shows basically the last, just above impact curves, about 5 or 6 kilometers above the surface on average. This shows these 3 panels. I'll show the same thing, relative brightness as a function of wavelength, with the data being the dots and the air bars being the vertical bars. And here we fit against a variety of water gas columns, grain radius, and water ice optical depth. And the water ice optical depth is listed in fraction of the total dust that's in the model to get this fit as well. So this has got dust, water ice, and water vapor in this particular model. And you can see we can generally quite easily actually get the model to fit the data very nicely. We see something like 2 e to the 16th water molecules per cc. That's consistent with our NIR observations, and quite a bit of water vapor. We see particle radiuses. It's harder to constrain, but I would say with confidence they're not submicron. Here's submicron, and there's some other fits you can do that makes you even warmer and fuzzier that that's the case. But you probably couldn't say much more about, gee, are they larger than 16? They're, best guess, best fit right now puts them in the 4 to 8 micron range. And then it fit against optical depth. We're seeing about 4 to 5% or so by weight water ice in this ejected cloud as it's coming down. And that's pretty interesting, I think, especially since this is 4 minutes after impact. So this summarizes some of these results. NSP2 did see the dust in the water as it came down, both water vapor, water ice. And in the final 20 seconds, so this is material that went up 15 or so kilometers, it's coming back down. Like I mentioned, we have some constraints on some of the sizes here. They're probably greater than a micron and less than 8 microns or 16 microns. The water ice grains they are. This is an interesting point that I'm not going to talk too much more about right now, but they have to be relatively pure to have lasted 4 minutes. And I'm not going to say what relatively means because that's some analysis that still needs to be, I think, completed. I call them water ice grains, and there's a question about amorphous versus crystalline. And that's something we're working into the paper right now, is we think you can constrain that with this data. That is crystalline water ice, and I won't go into the results from that. That's got to be finished up, but it is definitely water ice. Total water gas measurements are consistent with the measurements, and getting to the point I made about the scouring effect or a larger area effect is it's quite possible that this large impact scoured a large area, and this ongoing sublimation of water from exhumed ice is part of what we're seeing as we descend down towards it. We've got this kind of low, I don't want to call it a fog, but a vapor cloud coming up from the surface as we excavate into a much larger area than just a 20 to 30 meter crater. Now this is also very important, is I mentioned that we saw this nice ice signature very early on when the ejected cloud was brightest, and then it dropped off, and then we see water ice coming down at a concentration about 0.5% in the high angle plume. So what it looks like could have happened, or one explanation I'll get into here in a second, is we the high material, because it's got the higher velocities, most likely came from the top meter, maybe meter to 2 meters of material. So there is water ice there where we impacted in the top meter of regolith. And that was these grains I described with these NSP2 observations that went very high. And then there is a significant amount of water ice that is then below that as the lower angle ejected cloud came up and was excavated down to maybe as deep as 3 or 4 meters, maybe 5 meters deep, the low angle material might have come from. So we may be seeing a variety of horizons and different flavors of water ice at this site. And so when we try to take the preponderance of observations, not just from, I talked about the LCROSS observation, but also the LRO LAMP observations, which saw carbon monoxide and mercury and molecular hydrogen, and now they think they've gone back and looked again, and they think they see atomic hydrogen in the data following the Grail impact where they saw atomic hydrogen. They're like, okay, we better go back and look at the LCROSS data now. And they think they see it there now, atomic hydrogen in appropriate quantities, or consistent quantities with the Grail impact. I've kind of put together this quick little model for the LCROSS site, and most of you have seen this, where you have this kind of this frosty layer in the top meter or so that is what we're seeing in the high angle plume that's coming down. That's a mix of ice and potentially trapped gases. For example, the gases that LRO saw come out at very high speeds, the emission lines we see right at impact in our ultraviolet spectrometer is probably all material in that top meter or so of regolith. So there must be this kind of volatile rich, maybe fluffy material in the top meter. That fluffiness, I pointed out, was concluded from the flash duration of the near-infrared spectrometer. There's a physical explanation potentially that Phil Metzger has offered that it's actually thermal cycling that leads to the compaction of the regolith, and if you have this dust infall and other infall, that without that thermal cycling it will tend to stay more porous, and that could be why PSRs may be in general more porous than elsewhere on the moon, something worth thinking about and maybe testing. I note that here. And then there could be this deeper material that we've potentially excavated into with the initial low angle plume, and the ice and other volatiles that we saw in that initial low angle blast might actually be coming down from deeper, and the 2 or 3 where our impact actually excavated to much deeper. Down here is totally, incognito at this point. So one of the things that we wanted to do also with LCROSS, the LCROSS experiment, was to determine if the hydrogen we saw in the neutron maps was uniform. If it was, we impact somewhere, we see about 0.5% or something like that water, and where we impacted in Cabus. Or was it not uniform? And by uniform, I mean on the scale of what we impacted, right? That's all we could measure. But based on what we saw and the Lunar Prospector data, Rick Elphick's gone and he's trying to make the two agree with each other, reconcile the two observations. And he can by changing the desiccated layer between 10 and 15 and 30 centimeters or so, or 20 centimeters, I mean, of desiccation, matches the LCROSS data. Some combination of that along with changing how patchy it is. It's not that way everywhere, but it's that way here and there. And it may be associated with these double shadowed regions, or just, again, it's along the lines of these micro environments. Here's the LCROSS site. This is a near-infrared spectrometer, again, just before our impact. We impacted into this dark region right in here. The light coming from here, this is just scattered near-infrared light from the far eastern wall of Cabus, far away here and here. And so what we're seeing in here is an area that's receiving less scattered light from the walls. And maybe that, when you actually add up that area, it's about 20-40% of these dark areas. And that is fairly consistent with what Rick says you might need to match the LCROSS observations if you had basically a very small 10-centimeter desiccated layer. This can increase if you increase that desiccated layer, of course. So this may be one possibility for the LCROSS impact site, that it's patchy with you know, 1% or more water ice in the top meter or less, and then deeper down you got more ice-rich material below that. And with that, I thank you.